Okay, good morning. So in previous class we have seen the relation between the drain current and VDS voltage, that is the derivation of the drain current. There we observed that what are the different parameters affects the drain current. Okay. Now in this class let us see some important parameters with reference to MOS circuits like threshold voltage, transconductance, drain conductance, figure of merit, etc. Coming to threshold voltage, what is meant by threshold voltage? That is the minimum gate to source voltage at which the drain current starts to flow is known as the threshold voltage. In previous class, in the characteristic case, from the transfer characteristics, we observed that the transfer characteristic shows the relation between drain current versus VGS. Initially, when the VGS is 0, that is no gate voltage, that means the current also 0. But at certain VGS voltage, the drain current starts to rise. Wherever it is happen, that is called the threshold voltage. Okay. So after threshold voltage only, the channel will be existed between source and drain. So when the source is available, by the applying the drain to source voltage, you can observe the drain current flow in the MOS transistor. Okay. So that is the definition for the threshold voltage. It is very important and it decides the switching action of the MOS transistor also. Okay, that is if the applied gate voltage is less than the threshold voltage means no current flows. That means what? The transistor or the MOS transistor acts as a half switch. Okay, suppose if the applied gate voltage is greater than the threshold voltage, what happens? The drain current flow you can observe, that means the transistor acts as a on switch. Okay, like that the threshold voltage is very important point. Here the slide representing the expression for the threshold voltage, on what parameters it depends. Okay, just you remember this formula where the various parameters are. The QB is the charge density in the depletion layer under the oxide. Okay, in the depletion layer, the charge density is referred. Charge density means charge per unit area is referred as the charge density in the depletion layer under the oxide layer. Oxide layer means silicon dioxide layer. Then QSS is a charge density at the interface of the silicon and silicon dioxide layer. Okay. COX means capacitance, the gate capacitance per unit area. COX is referred as gate capacitance per unit area. And phi ms is work function difference between gate and silicon substrate. Phi Fn is Fermi level potential between inverted surface and bulk silicon. Okay, so like that different parameters on which the threshold voltage can depend, so you can see. And also let us see the formulas for different parameters. Like for QB, the formula is like this: square root of 2 into epsilon naught epsilon of silicon Qn of 2 phi Fn plus VSB coulombs per square meter. You just remember these equations. Okay, no need of derivation for this QB. Okay, similarly, where phi Fn is, you can express like this: KT by Q ln of Na by Ani in volts, where you know VSB is VSB. In previous equation we observed that VSB, that is substrate bias voltage. Substrate bias voltage. Small q is the charged particle charge of the charged particle, that is 1.6 into 10 power minus 19 coulombs. N is the impurity concentration. Okay, so based on the type of material, either p-type or n-type, the impurity concentration can be represented as Na or Nd. Okay. So epsilon Si is relative permittivity of the silicon. Its value approximately 11.7. And Ni is intrinsic concentration. Small ni, generally notation is small ni, it is intrinsic concentration. Okay, so like that we can see about the threshold voltage. Then coming to transconductance. Okay, before going to transconductance, uh, see the relation between threshold voltage and body effect. Okay, threshold voltage and the body effect. So what is meant by body effect means, in general, in the integrated circuits, okay, so more transistors are fabricated in the same silicon, right? So for the many number of transistors, the substrate is same. Okay, in the same substrate we are going to fabricate many number of transistors. Okay, so therefore what happens is the substrate potential, because of the substrate to or source to substrate potential of one device, the depletion layer in the in the channel region can be increased for the other transistors, so that they need high threshold voltage to switch on those MOS transistors. Okay, so that is of the that action is that effect is referred as the body effect. That effect is referred as the body effect. And see the relation between threshold voltage and VSB. VSB means source to substrate voltage, source to substrate bias voltage. Okay, so here the relation is changing the threshold voltage delta Vt equal to gamma of VSB, square root of VSB. Okay, square root of VSB or VSB to the power of 1 by 2. Okay, this is the relation. You just remember this relation also. If the body effect means increasing the VSB voltage. If the VSB is increased, the threshold voltage also increases. Okay, so to switch on the MOS transistor, we need to apply more threshold voltage or more gate voltage at the gate of the transistor, right? Where gamma is a proportionality constant and its value depends on the substrate doping, right? Now coming to uh, okay, here the typical values for the threshold voltage in case of enhancement NMOS case. Okay, its value is 0.2 times of VDD without body effect. VSB is 0 means there is no body effect. Without body effect, the threshold voltage is, we can express it as 0.2 times of the VDD. But with the body effect, suppose if the VSB is 5 volts, the threshold voltage requirement is 0.3 times of VDD. So more threshold voltage we have to apply. Okay. Then coming to another very important parameter of a MOS transistor is transconductance. Transconductance. Okay. Why it is also referred as important parameter is it affects the speed of the system. It affects the speed of the system. How this transconductance can be related to the speed, that you can see in the coming slide. Now, what is meant by transconductance? First define what is meant by conductance. Conductance is the ratio of current to the voltage. Okay, the ratio of current to voltage is known as the conductance. Now transconductance means that is the relation between output current to the input voltage. The ratio current to the voltage is, okay, one parameter. The current parameter in the MOS transistor is the output side parameter, whereas voltage is input side parameter. Since it relates input and output parameters, that's why it is called transconductance. Okay, so therefore here with reference to MOSFET, you can define it as the ratio of change in drain current, the ratio of change in drain current to change in VGS voltage. See, here is the expression GM equal to dou IDS divided by dou VGS when VDS is the constant. Like that you can define and express the equation for the GM. Okay, and see uh, on uh, which geometrical parameters the GM value depends. Okay, so you know dou IDS equal to dou Q by VDS, sorry, dou DS. That is, from the basic formula, current equal to charge by time. Current equal to charge by time. We can apply that basic formula here like this. Here, the change in drain to source current equal to change in the charge, that is induced charge, divided by tau ds. Okay, then where the tau ds is already we derived the tau ds, that is transit time for the charged particle, already we derived in the current derivation equation, that is equal to L square by mu VDS. Now substitute this tau ds in the above equation. Therefore, the changing current IDS is equal to dou Q VDS mu L square. Okay. Now let us see the change in charge. The change in charge is depends on the induced charge is based on the applied gate voltage, right? The amount of charge induced in the channel based on the applied gate voltage, right? Therefore, you can express the change in charge is like this. This is also from the basic formula Q equal to CV. Q equal to CV. So change in charge is equal to Cg into change in VGS voltage. So by changing the gate to source voltage, charge induced can be changed. Okay. Therefore, now substitute this equation in the above equation so that dou IDS equal to Cg dou VGS mu VDS divided by L square. Okay. Now you know already dou VDS by dou VGS is the GM, right? So GM equal to dou IDS divided by dou VGS equal to the rest of the parameters are Cg mu VDS by L square. So this is the equation for the GM, or it represents on which parameters the GM value depends. It is gate capacitance, mobility, the drain to source voltage, and channel length, right? Now coming to see the equation for the same GM in the saturation region. In case of saturation region, what is VDS value? VDS is, you know, saturation starts when VDS equal to VGS minus VT. Now substitute that one in the above equation so that you can express GM like this. GM equal to Cg mu by L square into VGS minus VT. So this is the another this is the expression for GM in the saturation region. In the saturation region, since Cg is the gate capacitance is epsilon A by D, that is the parallel plate capacitor formula. Cg equal to epsilon A by D. Epsilon means epsilon of insulator, epsilon naught. A is area of the channel, that is the channel width into channel length divided by thickness of the oxide layer, right? If you substitute in the GM equation, the equation depends on like this: mu epsilon of insulator epsilon naught W divided by DL into VGS minus VT. So the GM value is directly proportional to width of the channel and inversely proportional to length of the channel, like that. Okay. So what for all these means, it shows on which parameters the GM value depends. Okay. So you remember this formula also for GM in the saturation region. Okay. And also you can express the GM like this: GM equal to beta of VGS minus VT. Okay. But where what is beta? KW by L. Beta is KW by L. So if you know thoroughly the drain current equation representation in terms of K, in terms of beta, in terms of Cg, in terms of COX, then you can also understand easily the GM equation and its representation in different ways. Okay. Then from all these equations, we can conclude that the GM is directly proportional to the width of the channel, okay, inversely proportional to the length of the channel. So to increase the GM value, the width has to be increased, okay. If it is directly proportional, the incremental of that parameter increases the GM value, okay. Inversely proportional means decreasing that parameter, increasing the GM value, like that. Why we have to increase the GM value? If the GM value is increased, the speed of the system is increased, okay. How can I say that is? That we can see in the next one, that is figure of merit, okay. So before going to see the figure of merit, here one simple thing is output conductance. Notation is GDS, okay. So the GDS is output conductance, means output conductance. It is also a conductance, but related, taking the parameters of output side. That is, for the conductance, what is the conductance definition? The ratio of current to the voltage. Output conductance means output current to the output voltage. So dou IDS divided by dou VDS. Therefore, that equal to, from the previous equations, we can finally decided that the VDS is CG mu VGS divided by L square. Okay, you just remember, or you can derive applying the different derivations, previous derivations, right? Now coming to that one, figure of merit. Figure of merit notation is omega naught. For the figure of merit, the notation is omega naught, okay. It is a frequency term, actually, frequency term. The frequency term means, frequency term is inverse of the time, right? Inverse of the time. So omega naught equal to inverse of time, that is transit time tau ds. Already you know that tau ds is L square by mu VDS, right? L square by mu VDS. Therefore, the expression becomes like mu VDS divided by L square. But in the saturation region, VDS is equal to VGS minus VT, because the pinch off point starts at VDS equal to VGS minus VT. So that you can write the omega naught is like this, mu of VGS minus VT divided by L square, okay. And you can convert this one, this right side part of the equation, in terms of GM and CG from the GM equation, that equal to GM by CG. GM by CG. So therefore the omega naught is directly proportional to GM, directly proportional to GM, but inversely proportional to gate capacitance. So from this expression, you can say that if the GM is high, the speed of the system also increases. I mean high. If the GM is high, the system speed is high, okay. So always we need to have the fastly operating systems. So for that, what you have to do, you need to increase the GM value, okay. How the GM value increase? Previous equations represents on which parameters the GM depends, right? So for that purpose, we have seen all these parameters, that is improving the speed in what way, like that, okay. So this is about the parameters of the MOS transistors, some of the important parameters of the MOS transistors. Thank you.